Hi, y'all. So I am hoping that in between watching the first video that I posted on this chapter and watching this one, that you watch the Nat Geo video that I posted on D2L, which was only about 3.5 minutes long, but it's the top link in this slide. It has a number of different kind of applications of electromagnetic induction. The most shocking one, I think, is of course, the magnetic braking, which is pretty cool, and that's the way that braking works on a lot of amusement park rides, roller coasters, so on and so forth. Uses that idea of electromagnetic braking. Um, It's also used to damp out vibrations in experimental equipment. I use it in my lab to damp out vibrations. Um, let's see, what else? I think that's all I want to talk about right now. Although when I'm thinking about applications of magnetism, now I'm thinking about maglev trains, which I think maybe I talked about in the last chapter, but just wanted to mention maglev trains because if I haven't, I don't feel like I've done my job. Anyway, what I want to talk to you about today is the concept of magnetic flux. And we've heard that word before, that word flux before, when we were talking about electric flux and Gauss's law. And we remember that flux is just a fancy word to mean flow. So in this particular slide, what we see here is we've got some loop of wire, and then depending on the way that loop of wire is basically stretched, it changes the number of magnetic field lines that are penetrating through that area that coil encloses. So what we're going to do is we're going to try to quantify this magnetic flux, this, I guess, flow of magnetic field through this area. And the way we do this is with this formula here. This says that magnetic flux is equal to the magnitude of the magnetic field times the area of this surface that the field is penetrating times cosine phi. And that angle phi there is the angle between a perpendicular through the surface and the magnetic field. All right, and the SI unit of flux is the Weber, which is abbreviated WB. That's for Weber, not Warner Brothers. WB. All right. Yeah, I'm it's too easily distracted even when I'm talking to myself. That's pretty bad. All right, so I'm going to stop this. I'm going to pull up. Okay, so let's say I've got some coil here that if I was thinking, okay, there's my coil. All right, there's a perpendicular to the coil right there. All right. And let's say we've got some magnetic field here. How am I going to do this? Some magnetic field there. There we go. That's penetrating this coil. So my flux would be literally the area of the coil. So I would need to do pi r squared and know the radius of this disk. So pi r squared times the strength of the magnetic field times the angle there between my silver pin and my yellow pin. The silver pin is the magnetic field. The yellow pin is the normal, the perpendicular to the area of my loop. All right. Let's go back to the PowerPoint. Maybe we'll see. Okay. See if I'm successful. Hopefully, I am. I won't know about it until later. All right. So there's our formula. Weber is the unit for SI unit for magnetic flux. All right. We can see that that if I've got my coil there, and I've got it basically so that the perpendicular to the coil is in the exact same direction as the magnetic field, then I'm going to have all kinds of field lines penetrating through there. But now as I start to twist this, keeping the magnetic field basically towards the camera there, as I start to twist this, I can imagine that I'm going to have less and less and less field lines penetrating this guy. And that's what's going on in the second image in the middle panel. Until when I twist it all the way so that my perpendicular to my coil and the magnetic field is at a 90-degree angle, what would I have? I would have no magnetic flux through my coil. Right. Great. So the magnetic flux, just like with electric flux, it's basically proportional to the number of field lines that are penetrating my surface. So let's go back a slide and let's look at this. Flux is equal to magnetic field times area times cosine of phi. So if I decrease the magnetic field, I'm decreasing the flux. If I somehow manage to shrink the area of my coil, if instead of having a solid copper disc, maybe I've got something that's flexible and I shrink the area somehow, then I'll be decreasing the flux. If I alter that angle phi so that it's not 0 degrees, so that it's, I don't know, somewhere between 0 and 90, I'm decreasing the flux. So flux is a function of magnetic field, area, and then the angle between my magnetic field and the perpendicular to the area, or the normal to the area. All right, great. That's interesting. Let's go back one slide. What happened to my, where am I? What happened? How did I deleted a slide. Okay. This is me now pausing this video. How do I pause the video? I don't know. This is awful. This is horrendous. This is a couple other words. Okay, I'm going to pause this. I'm going to fix that. I'll be right back. I'm back. Were you worried? All right. So I don't know what happened there, but here's the slide that was supposed to. Here's the slide that was supposed to be there. All right. So we have here basically a circular loop of wire that's got some small radius, 0.5 centimeters. That's 5 millimeters. It's actually pretty tiny. I don't know. It says that this circular loop of wire is inside a solenoid. And remember, what's a solenoid? That's like we've got a cylinder and we've got a bunch of wire wrapped around it, so that we've got wire basically shaped into a cylinder. That coil of wire is at a 20-degree angle with respect to the axis of the solenoid. All right. We're given the relevant information about the solenoid, and we're asked to calculate the magnetic flux through this little circular loop of wire that's inside the solenoid. All right, so that's our goal. Let's see if we can figure this out. All right, so I'm gonna draw. Okay, so first off, solenoid. So it's like I got a bunch of wires there wrapped around some cylinder, and I've got current running through the wires. I don't know, maybe current's going this way. Okay, if current's going that way, I can pull out right-hand rule number 2. Let's see, if I'm thinking about this solenoid, the side that's closest to me has current running to the right. Okay, so the side that's closest to me has current running to the right. My fingers go to the right. Inside the solenoid, the solenoid there, my thumb goes to the right. Inside the solenoid, my fingers are pointing up. As a result of having current running through the solenoid, I'm going to end up having a magnetic field that's basically upwards. There we go. All right, so also inside the solenoid, what do I have? I've got basically a circular loop, something like that. and that circular loop is making a 20-degree angle. I gotta find another color. The perpendicular to that circular loop is making a 20-degree angle with the axis of the solenoid, or in other words, also with the magnetic field that's in the solenoid, because the magnetic field is going to be along the axis of the solenoid. So there's our problem, and I've got to switch off that green color because, frankly, that's just not pretty. Call that, well, no, I won't say what I was going to say. Should I? No. Okay. So let's figure this out. B is equal to mu naught N I. That's the magnetic field inside of a solenoid. Do we have all that information? Let's see. We've got the current. That's 5 amps. And we've got that small n too. Small n is the number of turns per unit length of our solenoid. So that's literally, it's the number of turns per meter. So I've got all that information. So we can plug this in. B here is going to be equal to mu naught times 12,000 turns per meter times 5 amps. And when we do the math there, we get a magnetic field that's 0.0754 Tesla. Cool, so we've got the magnetic field. Next step is to figure out the flux. Let's see, we've got our magnetic field. B is equal to 0.0754 Tesla. Let's give ourselves a little bit of space, so we'll hold on to that idea. We'll hold on to that number. This is worst eraser ever, my word. This is just like the whiteboard at school, right? Can't get it to erase. All right. So let's see. We want to figure out the flux, which if we want to, don't, what, eraser, stop. What are you doing? Flux, there's that symbol for flux, is equal to B times A times cosine of phi. Area, well, our fuchsia or purple or whatever it is loop there is a circle. So the area of a circle is what? It's pi r squared. Do we have r? Yes, we do. R is what? 0.5 centimeters, but of course we don't operate in centimeters, we operate in meters. R is 0.005 meters. So now it's just a question of plugging and chugging our way through here. B is 0.0754 Tesla. The area is pi r squared. And the angle between the perpendicular to the surface of our coil and the axis and the magnetic field is 20 degrees. So the perpendicular to that coil and the magnetic field there make a 20-degree. The camera's in the center, not on the right-hand side, you idiot. I'm talking to myself. There we go, 20-degree angle. All right, so plugging this into a calculator, what do I get? I get a fairly small number, but I get that my magnetic flux is 5.56 times 10 to the negative 6 Weavers. There we go. And that does it for that.